Hello, my friends. This is Dr. Mohamed Nezami again with another video on the design and modeling of RF systems and devices. My friends, my last two videos were on the design and modeling of small cell transceivers. One was the 3.5 gigahertz one, which is categorized as the as one of the sub-6 gigahertz 5G small cell transceiver. The other one was a 28 gigahertz. Okay, so in here you can go back to these videos. I've detailed the design and analysis of the these RF transceivers. And as a first step in designing a circuit board for this small cell RF transceiver system, we would use Pathwave to do a system analysis. And based on that, we have chosen parts from off-the-shelf components that you can purchase from distributors on Alibaba, Chinese, or Mauser and DigiKey. And so we have put together these systems, and I did the analysis, the linear and nonlinear analysis of the chain, both the receive path and the transmit path and receive path. And at the time, of course, we did not mention that we could, if we have the baseband section, we could play a waveform, 5G waveform through the entire RF board to observe the characteristics of the behavior of the RF chain in terms of error vector magnitude, spectral containment, and other things as well. We could also perform BER as well. So today, what I've did is let's go back to one of these systems, which is the transceiver, this transceiver here, which was 64 elements, 8x8 beamforming, 28 gigahertz MIMO system that I have designed in the previous video. And you please go back to that video and watch it first so that you could continue. So what I'm going to do today is we're going to go back to this system here and stimulate it with construct a baseband section, which is starting from binaries, ones and zeros, and encode them, modulate them, do the digital signal processing so that it could play as a real baseband stage, and then observe that. So, and I've done that already here. So realize from last time, this was the transmitter section that I did last time for the 28 gig. And if you see in here, what I did is I removed the receive path. Okay, so this is the system that I've done last time, starting out from the DAC in here, where we have chosen a balun and then a filter, a fixed attenuator, an amplifier, a filter, and then we have an up converter section in here. This is an up converter section with the LO in here, and all the components were chosen for that. And then we go into the distribution, the passive distribution stage in here, okay, and then onward to the final beamformer chip in the transmit path section. And we have chosen that we're going to drive these elements with 13 dBm, okay, on each element at the time to fulfill the 50 dBm EIRP. So what I did next is take this RF system, and now we're gonna basically, let me close some of this because it looks like the memory system is running very slow here. Okay, so what we did here is I took the RF system in here, okay, which is this one in here, as I made a symbol for it, okay? So if you go to this one here, and if you open it, you basically, that's what this is. So we're gonna take this thing in here and put it in here, and then drive into it signal that we're gonna generate with the digital signal processing. So we have, this is a DSP modulator that modulates QAM signal. And as this time it's setting for 64 QAM, 200 megahertz bandwidth. So we're starting out with bits, random bits, ones and zeros, and then we gray encode them and then map them into symbols, QAM symbols. And then we're gonna take the real and imaginary and shape them with two FIR filters, okay, to do raise cosine so that we can shape the spectrum. And then we're gonna oversample them, okay, and then go through the modulator in here, okay? And then at the same time, we're gonna observe the signal at the baseband, okay? After that, we're gonna take this signal, and of course, realizing that this is numerically generated, we have to set the noise floor to mimic the DAC power spectral density, which is at this point, as you recall, the 9081 chip from ADI, it had a minus 155 dBm per hertz distribution. So that's what this block here, and that's what we're setting right now, minus 155 dBm per hertz. Okay, and then we're going to feed that signal into the entire system, which is this is what was designed in video 6. Okay, so and then we have a bunch of monitoring things in here. So the first one is we use a something that is similar to VSA, okay, vector signal analyzer. It's a this block here, okay, so it's a digital demodulator which you can display a whole set of key indication parameters like EVMs and the real and imaginary, the spectrum, the constellation, and so the eye diagram. And then we're going to also demodulate the signal and calculate the EVM, okay, the error vector magnitude, okay. And at the same time, we're going to measure we're going to monitor the spectrum and then measure the power by putting the sink, which observes the signal and calculates the average power from it, okay? And the average power right now, and this one is sitting at 12.987, okay, which is what we intended for each one of those elements to be driven by 13 dBm. Well, furthermore, we also have a CCDF, which is commutative distribution function. And what this does, it actually looks at the signal and does statistically calculates the peak power and the average power. And so you can get an idea on the amplitude envelope distribution of the signal or the power distribution of the signal so that you can basically measure the peak to average ratio, okay? Now that one, even though I've done it here, but really we were doing it also right before at the DAC, okay? And that's useful because we can observe the peak to average ratio so that we can back off the DAC or the signal of into the up converter so that we don't cause any nonlinear saturation. So let's get back and let's talk about the theory on this. So we're gonna, and then we'll come back to this. So let's put a detail on this. So now again, this is Dr. Mohamed Nezami. I'm an RF consultant. I design RF boards. So if you have any need to offshore, offload your engineering effort in designing RF boards, let me know. You can contact me at this number here. I operate out of Jerash, Jordan. This is my email, and this is my phone number via the, if you don't have access to international calls, you can call me on the WhatsApp and the Telegram. Okay, these are apps that you can utilize. So if you have any need for RF board design, board level designs, I work with you. I'm very reasonable. Right now, I'm running a special on any effort below 1,000 hours. It's $20 per hour rate. Okay, so I take your design and work with you. I would do the system design, pick all the components, do the bill of material, do schematics and BCB also. So all you have to do is just you get the board Gerber files with the bill of material, with the artwork, with the report on the design, and then I work also closely with your team in system integration and assembly, BCBA, and the testing as well. So, like I said, today we're going to talk about the baseband suction of an FR2 5G mmWave MIMO transceiver with beamformer, which is the system that I have designed in the last video, video number 6. So in video number 6, as you recall, we use the 9081 ADI chip, which has 4 DACs and 4 ADDs, and we are implementing 4 transmit, 4 receive, dual pole, mmWave F2 subarray dual pole. I repeated that. But we are designing this system here where we are doing 2 panels. Each one is 64 elements, and each one has 2 transmitters, 2 receivers. Now, this one here, it's a dual, all the antennas are dual cross polarized. So we have this one here is 2 transmitters, 2 receivers, not at different frequencies, but these are the same frequency, but different cross polarized. Okay, one is at the plus vertical horizontal, you might want to call it, if you don't want to call it, plus minus 45 degrees. And here's the other one. Okay, so each one of these is actually 50 dBm EIRP. And you can see here what we have. We have the system, we take the signal out of the DACs, we go from balanced to unbalanced, and then go into filtering, amplification, up conversion, filtering, amplification, and then we go into a transmit receive switch, basically, that collects the signal from 64 elements. The beamformer chips are here. There is 16 of them, 16 chips. So we have a passive distribution divider in here that divides this signal among 16 beamformer chips. Or in the receive path, we have a combiner that combines the signal from 16 beamforming chips. Okay, that's done both sides. Now, here's the chip that we're using, which is the ADI 9081. And since we're doing only the transmitter section in this presentation, so the main characteristic of the performance of this chip is the main important ones is that it's running at 12 gigasamples per second. Okay, it has a JEDIS 204B on the back here to support the SerDes. Okay, and then we're going to generate out of this, like we did in video number 5, which was designing a sub 6 gigahertz small cell transceiver. So where we designed it based on this, where we're going from these bits to antennas, directly from the DAC to the antennas, no frequency translation whatsoever in either path, the downlink or the uplink. Now let's see what else. The full scale on this, or the full scale power on this one is a few dBms. So, but we're gonna generate, we're gonna run it at minus 13 dBm. Okay. The power spectrum, the noise spectral density on this one here is minus 155 dBc per hertz. Okay, so we're going to use that as a point in which we can basically trace the signal to noise ratio throughout the entire system from this chip, from this here to the antenna. Right now, we're not worried about the receive section because that's for another session. So let's get back and calculate the EIRP for this system here. We have 4x4 MIMOs. Well, it's 2x2, but There's another 2x2 that is cross-poled, so total 4x4. The number of elements is 64. Okay, the frequency is 28 gigahertz. We're assuming that we have a unit cell antenna with a 3 dBi. Sorry, this should say dBi, not 3 dB. 3 dBi gain. So that makes the entire plate or the entire tray, basically the array is 20 dBi gain, total gain. So we took 10 log of 64, added to a unit cell, and that gives us that number. Now we're going to run the beamformer chip PA with a 13 dBm, okay? And the chip we have chosen is from Renaissance, which has 8 IOs, 8 beamformers, 4 of them for one polarization and 4 for the other polarization, okay? Each one of those, we're going to run it with 13 dBm. So which means that the total power basically is 31 dBm from the entire panel, okay? Now, take this number, add it to the array gain, and basically you get the number for the EIRP, which is about 52 dBms. So let's assume that we're going to have 2 dB allocated for losses for the antenna feed. So that means that our EIRP is 50 dBm. And that's very much is the commercially broadcasted number for these systems. They sell them as 50 dBms for small cells. Okay, which will allow us to communicate with a tower that is, say, 3-story building mounted on top of 3-story building or 2-story building, up to like 1 kilometer reasonably. So let's do an estimate for the receive path now. I know that we're not concerned about the receive path, but just so that we include it as well. So if we use this system at 50 dB EIRP with 64 elements, with 21 dBi gain for the array, the RX signal, if you look at the Rappaport report on mmWave 28 gigahertz experiments, you're most likely going to get minus 60 dBm at the at somewhere between ½ kilometer to 1 kilometer. So, and of course, if you're running 64 QAM, that requires you with an EVM less than 8%, and the SNR is around 22 dBs. Okay, so and realizing that the Renaissance chip that we have chosen, that you can go back to video 5 and 6 and see the details on that chip, the receiver noise figure is about 8 dB. So that means the receiver sensitivity is the noise floor into 1 hertz bandwidth minus 174 dBm per hertz plus the noise floor plus the integrated over the bandwidth of 200 megahertz, okay, which is minus 83 dBm. Now, so realizing that at the minimum detectable signal we would want it is really the SNR on top of that number here. So that means we're minus 61. I'm sorry, I forgot the minus sign on here. It's minus 61 dBm. That's basically what's the signal level at the edge of the cell. Now with the ADD on the ADD and the chip in here for these ones, if this is setting at, we're going to drive it with say minus 10 dBm. With minus 10 dBm, that means now you take this signal, which is minus 61 dBm, you need to amplify it by at least 51 dB, 50 dB, and that's the overall gain of the receiver. So now you got to add some variable gain out of this. You're going to make at least say 20, 30 dB out of this is variable, because this is really at the minimal detectable signal. So you could you're going to have much stronger signal as you get closer to the cell transmitter point. So in which case you're going to have to reduce the gain. So so that naturally that's what you're going to do, is you're going to have a variable gain in there somewhere. Now let's estimate the transmitter gain, just like we did. We know that we're going to have the Renaissance chip. We're going to run it at plus 13 dBm, okay, and it has a transmit gain of 20 dB. So really, if the DAC, this DAC that we're using here, if the full scale is about 4 dBm for CW, okay? Let's run it at minus 13 dBm for our 5G signal, which has about somewhere between 8 to 12 dB peak to average ratio. So depending on the QAM level that you're transmitting and the shaping, the kind of filter that we're going to use. So let's run it at minus 13 dBm. If we're going to have an output of 13, minus 13, so that means your transmitter really has to have a gain of 26, and that's what we're going to show. Now, let's review what the transmitter noise floor is from the DAC to the antennas. So we're starting out from the DAC to the output of the beamformer onto the antenna feed line. We want to trace the noise floor, and while observing the signal, the desired signal levels. Like for instance, in this case here, the noise floor of this DAC here is really is at minus 155 dBm per hertz, okay, or dBc per hertz from full scale, okay? So what that says, then this one here, we're running at minus 13 dBm. So you can see that we can integrate over the bandwidth of this NSD here and calculate the noise to signal ratio. And that's what we're going to do for the entire system as we walk through the whole transmitter. So the noise floor for the transmitter is really defined as if it was not from DAC, but if it was from just a 50 ohm noise from at room temperature, it's minus 174 dBm per hertz plus the integrated over this bandwidth. So ideally, if we have a 200 megahertz and for the transmitter, and we have a noise figure of 14 dB. Where did I get this number? This was the number. This is a number that we have basically for the entire system, as I will show from last time that I showed you that we have a noise figure on the transmitter side for 14 dB, okay? And of course, the transmitter gain is 26 dBs. So at the output of the transmitter, the noise floor is going to be minus 51 dBm. Of course, that's the noise floor theoretical number. Now, of course, the signal level is 13, plus 13 dBm. So plus 13 dBm to this, so that would be your signal to noise ratio. Now, for the DAC, this, of course, the transmitter is not going to be operating with minus 174 dBm per hertz. It's going to be much worse than that. And that number is, we're assuming, as an assumption right now, it's minus 155 dBm per hertz. So if you integrate over the bandwidth, that's minus 72 dBm out of the DAC, okay? Now, which says that if the DAC is transmitting minus 13 dBm, that's what we're going to intend to have it run at. If you subtract that number from this, you get, that's your DAC SNR output. That's 59 dB, okay? Now, with this DAC here, let's do the same thing in here. Let's see what the noise floor would be at the output of the transmitter. That would be minus 155 dBm per hertz, integrated over 200 megahertz, degraded by 14 dB, which is a noise figure for the transmitter, plus the 26 dB gain, because that gain, of course, from the DAC to the antenna, we assume that we're going to design the system for 26 dB. So that gain is for both signal and noise. So we end up with minus 32 dBm in this case. Now, minus 32 dBm, of course, we're going to try to run the system at plus 13 dBm out of the beamformer chip. So plus 13, plus 32, that's basically your signal to noise ratio. And that's this number here, which is 45 dB. So we're going to take the beamformer output, which is 13 dBm, and the noise floor, that is theoretically going to be the white noise floor of the system. That's, you're going to get 45 dB of signal to noise ratio. So you can see the signal to noise ratio degrades from the DAC output, which is almost 60 dB to 45 dB. Okay, which is, again, that's just the noise figure number, really. So here's the block diagram that I obtained, that I borrowed from the people at Renaissance, which shows that you have a baseband processor. And in this video, that's what we're going to detail in here. Last time we did go through, analyze this system in here, where we have 64 elements, dually polarized with 16 beamforming chips, okay? And then we have vertical and horizontal divider summing network for both transmit and receive. And then we have an up converter section that took the 3.5 gigahertz from the DAC and then up converted to 28 gigahertz and then split that signal in the transmit path. You split that signal, of course, for both horizontal and vertical to distribute to the 16. And that's this chip here, of course. That's the block diagram of the chip. So one polarization is color coded with the blue here, and the outer two are for the other polarization, of course. And this is the up converter path and the uplink and downlink, of course, in these chips here. So in video number 4, I designed the 16-way splitter. We need to split the signal from the DAC to 16 beamforming chips, okay? And then at the same time, we will, it's not just a divider in the transmit path. When we switch over to the receive path, it's really combining the other way. And so we got this part here. These are thin film 4-way dividers they are available from Knowles and from many circuits. And this was cascaded in here, and this is the performance we got based on the S parameters that were provided from the manufacturer of this. So we're going to tend to use this as the feed design. Now, you could, if you want, design this as a Wilkinson dividers and use no parts like this, just a strip line with thin film resistors embedded. But it's up to you. So I just chose this because it's plainer and just for the heck of it, it's just simpler. Now, last time, this is the system that we designed. So we took the from the sub 6 gigahertz transceiver front end, and I added an up converter and a down converter, and then we of course we have the 16-way feed network, which took the signal split as 16 ways to go into 16 individual beamforming chips. And in here, I just showed 2 beamformers. The others are terminated, and the other ones are open. I just took 2 out of 16 beamformer networks and just basically eliminated those and just used 2 beamformer chips models, one as a transmit and the other one as a receive path. So, and that's what we have in here. And I did the analysis. You can refer back to video number 6, and you will see how this thing works. Now, in this session, so let's focus on the transmit path. So what I did is I removed the receive path in here, okay, and that's what I did. You see that I only chosen the uplink path, okay, with just 1 out of the 16. I left these open because I didn't need to terminate them. It's well isolated, and so it doesn't really impact me very much. So we're going to take this and replace this signal generator in here that we use to test the entire chain with a real 5G signal modulated and do co-simulation. Co-simulation means you can actually mix between, you could take an RF chain and a digital signal processing chain and put them together and co-simulate and actually trace the signal throughout the entire chain from bits to beamformer output at the antenna feed point. This is a run for this chain in here, just showing you the conversion gain and the noise figure, is it? Let's see, this is cumulative noise figure, CNF, and cumulative gain. And that's basically what you see in here. Here's the chain. And so we're getting about 14 dB noise figure for the transmitter. And then we're getting about 26 dB of gain for the entire system, running from the DAC point to the beamformer output point, okay? Now, let's do some calculations with this system. Let's take this system here, and at room temperature, if we were running just plain thermal noise through the system, like I did before, if you look at the, so what I have here, I have a marker at the beginning. This is supposedly the DAC point, okay? And this is the beamformer output. This is where you're getting the 13 dBm signal. At this point in here, the DAC output was minus 13 dBm. So the desired channel power, which is DCP here, that's this here. You could trace a signal that goes through this chain as it gets from minus 13 dBm all the way until it gets to plus 13 dBm, okay? And what I did here is I traced the channel noise power, okay, and the carrier to noise ratio or carrier noise power. Okay, so let's do that. So at the beginning here, we have minus 91 dBm, and that number in here was calculated based on this because we have minus 174 dBm per hertz is the wide spectral noise density at room temperature. Integrated over 200 megahertz, that gives you about minus 90 dBm, which is this number at this point here, okay? And then this noise, as it goes through the system, of course, degrades by the following. So, well, even before we do that, assuming that we have a 13 dBm signal in here, minus 13 dBm out of the DAC, minus 90, that gives us 77 dB as the carrier to noise ratio. That's the CNR in the blue here. Okay, let's go to the other side now. The noise floor will be this much power spectral density, dBm per hertz, degraded by the noise figure of the entire system, which is 14 dB, integrated over 200 megahertz, which is our channel bandwidth. That's what we're going to run the 5G waveform at. And that gives us about minus 51 dBm. And that's this number here. As you can see, that we just verified computational with simulations to validate the chain. So if you do this, then the SNR at this end, at the beamformer output, is basically we got plus 13 dBm. That's the channel desired channel power. We subtract from it the noise power, and we end up with 64 dB at this point. That's signal to noise ratio. Of course, we won't get that from an actual system because we really, the DAC has much worse noise floor than, noise power spectral density than a 50 ohm resistor at room temperature, which is minus 174 dBm per hertz. We have minus 155 dBm per hertz instead. So now let's use a real DAC in there and let's calculate the system parameters. And I've done the same exact thing like this here, except I changed the noise power density at the input of the transmitter with minus 155 dBm per hertz. So you end up with minus 13 dBm DAC signal, and the noise power would be at the beginning is minus 72 dBm in the 200 megahertz, which means your signal to noise ratio is around 60 dB. That's what really the DAC system has at the beginning. It's about 60 dB. Now let's go to the other end, right at the input of the antennas elements. We have 13 dBm out of each beamformer, but the noise floor is really minus 32 dBm, and that is why. It's because the minus 155 dBm per hertz from the DAC gets degraded by 14 dB, which is the noise figure, and then gets integrated over 200 megahertz, and that gives you minus 32 dBm. So between minus 32 dBm and plus 13 dBm for the desired signal, the carrier to noise ratio is 46 dB, just like we have calculated here, which is close, 45 dB. There's a dB difference somewhere in the chain in here. You can adjust for that if you like, but it's reasonably okay for right now. So now, why do the ultimate goal is that we have a transmitter, and then we have to validate the transmitter in the simulation as if it was on the bench. If you have a transmitter on the bench, usually what you want to, the main characterization points of the system is you want to check the EVM, the error vector magnitude. Of course, depending on the modulations, this percentage of that error vector magnitude varies, okay? And it depends on whether you're running FR2 or FR1. The FR2, the highest modulation level is 64 QAM, and that's 8%, okay? So that's what we're going to do today is run this system with 64 QAM and observe the EVM. At the same time, look at the spectral regrowth from the transfer, because the 3GPP committees, they give you a spectrum envelope that you have to comply with for this transmitter. So in addition, also, you have to make sure that your adjacent channel power, which is specified also, is fulfilled. So you go, let's say that we're running right now 200 megahertz channels. So you go 100 here, 100 here megahertz, a center of the channel. You go away from that to the next channel and make sure that the spectral leakage from your current transmitter is below a certain level that is specified by the committees of this system. So that's what we're going to try to do in simulations as well. In real life, on the bench, you have the vector signal analyzer from Agilent Technologies or Roden Schwartz, and so you could take that equipment and set it up, and it would measure those things for you. But in here, we're going to estimate that using simulations as well, because what we're trying to do is make sure that the system level design is going to pass hardware implementations, okay? Now, if you look at the waveforms for both the FR1 and FR2, or the sub-6 gigahertz 5G waveforms and the millimeter waveforms, basically the systems differences are listed here. Of course, in this it retains the 4G LTE stuff, but we're not interested in that. We're interested in this here. The main thing is that if you look at the modulation levels, we have all the way to 256 QAM. Okay, so we're going to run at 64 QAM, and that's usually the system for FR2, the millimeter. Okay, and of course, the signal generation is really not just plain quadrature amplitude modulations. It's really an off-DM signal. So meaning the signal is orthogonal multi-carriers that are modulated, that contains preamples, midamples, and pilot channels and pilot symbols. So it's a very complex signal. But at least for right now, what I'm going to do is I ran two versions of this. I ran one base band suction that I have built up from discrete components, and it just plainly random 64 QAM signal. I didn't worry about the regenerating and shaping it as an OFDM signal. As you know, when you the OFDM spectrum for the 200 megahertz channels is not going to be the same as really the 64 QAM with a fur filter shaping. So it's a little bit different, but it's close enough. And the reason for this is because, as I will show you in a minute, is because if you're going to use a real 5G waveform, then you really have to demodulate an entire 5G signal. And so you want to make sure that you're not impairing. How do you isolate and look at the transmitter alone impairments in terms of EVM and in terms of power spectrum and other things? So what I did here is I started first is running just a plain 200 megahertz channel of QAM signal, okay, and trace the EVM throughout the system. Now, I don't have a license for the 89600 VSA. You can get that to run in your Pathwave SystemVue. I don't have a license for it, so I couldn't run it. It's this block here, and you can see this. This is available in the. It has a separate license, so. But I'm going to run the built-in demodulator from the Pathwave, and that's good enough because it shows me very much the same things. Okay. So, and also they have another function in here, which is the 89601, which is entirely for VSA 5G in our modulation analysis. So you could utilize this one as well. So I don't have license for these systems, two separate licenses. So what we're going to do is we're going to take the transmitter that I designed in the last video, which is this one here, put that here into a whole back-end digital signal modulator that mimics a 5G 64 QAM signal in 200 megahertz bandwidth. Okay, so what I've done is generated the 64 QAM. I'm going to observe the baseband signal in here. Took with the spectrum analyzer and put it on one of the real or imaginary. I don't remember which leg is this. Doesn't matter. You get exactly the same thing. And so what I do is I take this signal. This is pneumatically generated, so the noise floor is infinite. So or whatever the word length of the 64-bit in here. So I want to fix first. I want to fix the power spectral density of the noise floor of the waveform so that it actually replicates or mimics the power spectral density out of the DAC that I'm using. So, and that's what this block here. And then I bring in this entire RF system here. Notice now, this is co-simulations because this is digital signal processing running at sample rate, symbol over sample, so sample rates. And then this is an RF chain. So I bring in this RF chain in here, and then I would play through it, this 5G waveform. And then I grab the output and take it into a demodulator first that demodulates and calculates the EVM. And then I take it into another signal analyzer, which displays real, imaginary, displays the constellation, displays a whole variety of stuff. And I have a spectrum analyzer in here to monitor it, look at the spectrum. And then I have a sink in here that syncs the signal in and computes the power. In this case, you can see the number in here when I grab this. It's 13 dBm, and that's really what we want. We want this signal in here to be 13 dBm, because that's what we designed the system. Is minus 16, and that's this point here. Of course, I do have the same thing almost for the DAC output, for the power spectral density. So you calculate the power in here, it's minus 13 dBm, okay? So in here, I do the same thing. I look at the EVM out of the DAC, and then the spectrum analyzer, and the modulation analyzer in here. So what I'm doing here is I'm comparing the modulation integrity out of the DAC compared to the out of the PA of the beamformer chip in here, and that's what you're going to see shortly. Now, so starting out with this signal in here, this is the starting out with random bits, gray code them, pack them into symbols, take interleave them so that you have real and imaginaries, oversample them, and filter them, of course, in here, oversampling them, because that's what happens in the DAC system. Okay, and then do the modulation at 3.5 gigahertz. So that this thing in here, output in here, this here is a baseband, of course, but this output in here is 3 gigahertz. And you can see here's the baseband signal. Okay, and right now it's 100 megahertz, which is 1/2 of the channel. This is the imaginary only, not the real. It's one leg. And the other leg is the same thing, so spectral inverted, and you get complete twice that, which is 200 megahertz. So this is the system in here. So, and that's basically what I will show you in a minute. We're going to go into that. If you look at the DAC output, this is the DAC output again, showing you the spectrum. Okay. This is the output of the sub-6G DAC, okay, before setting the noise spectral density at 3.5 gigahertz, okay? And then, of course, this is when we set the noise floor. So I'm going to set the noise floor just like we estimated in the chain in here. So that's where we estimated, we said that the TX SNR N is going to be 59 dB, 60 dB almost. And that's what you see in here. That's 60 dB. So this is what goes into the, what's going to go into my, this is the IF output of this entire system in here, which is basically this here, which is my video number 6 block. So we're going to go into this, and then of course this is the output of the PA at plus 13 dBm, and we can see that the noise floor from of the system in here, if you compute from the plus 13 dBm, you have 47 dBs, and that, if you go back to the this here, and that's what we wanted to do. See here, we have 13 dBm out. The noise floor is going to be minus 33 dBm in here, and the output is 46 dB of signal carrier to noise ratio, in this case, computed and calculated. And that's what we are getting actually with the actual live modulations. And so, and then of course, we're going to monitor the EVM out of the DAC in here, which is almost ideal. This is because this is really before I set the noise spectral density. So it's just almost ideal, 0 EVM. And the SNR, of course, is 60 dB. Here it is almost 60. Okay, that's what the system is seeing. This is a the modulation analyzer of the Pathwave, which I will show you in a minute, running live. And of course, this is the out of the PA. You can see here that the EVM really is about 7.7%. So we're almost right there. We said that we wanted, usually it's less than 10%. So, and then the SNR in here, the QAM SNR is about 24 dB. And of course, you display the spectrum. So this is the baseband, the IF, and then the IF with the noise spectral density out of the DAC, and then finally the PA. Okay, now that's one way of running this. I have another way of running this where you actually can use the built-in new radio downlink source from the Pathwave. This one here actually generates an actual OFDM signal, a real signal. And I ran the same thing and it gave me exactly the same response, except I really couldn't check the EVM because I have to completely demodulate the signal. And unlike the demodulator in here, this demodulator in here is working on QAM, so it's synced. There is no palettes, there is no overhead symbols, there's no palette carrier. So in this system in here, it was easy to demodulate and get the results fine. But when you have a real 5G signal in here, you can't just straight go into a demodulator, 64 QAM demodulator. So the only thing I was doing is basically looking at the out of the DAC, which is minus 13 dBm almost, and out of the beamformer chip, which is plus 13 dB. So let's look at the system. So basically, this is so this is basically right now is the digital modulation section. This is the setting the noise floor. Like I said before, it's setting right now at minus 155 dBm per hertz. And this here, this block here, is really this block, which is the basically the RF transmitter that is running here. Okay, so we've got the entire transmitter section that was designed in video number 6. Okay. So, we can look at the budget link. So again, this is 26 dB gain, and the noise figure is 13 dB. That's basically okay. Let's look at the budget link calculation for the simulation for the, this is just running the RF section. This is not running it with the DSP section yet. Okay, and the same numbers that I showed before, we're getting the output SNR is about 46 dB, while the input SNR out of the DAC is 60 dB. This we did show this in video number 6, so there's no need to repeat it. So this is the signal for the out of the baseband signal right now. Okay, And then, of course, this is the IF signal dumped to the files, and that's where this is the IF with the noise spectral density, and this is the PA. Okay. Now, the if you look at the system in here, what I do is I measure the power at these points in here. You can see that I measure the power in here. And when you look at this here, I have a sink to the signal, a sink that grabs the signal file. And then what it does, it computes as an equation, okay, the average power, okay, and the average power really is computed through a MATLAB equation in here. That what it does basically, what I do is I define the dBm computation into 50 ohm resistor, okay, and I take the signal and basically take the absolute value, and then I take the mean average divided by the square it and divide it by 50 hertz, 50 ohm, and you get dBm value that corresponds to the power level, and that's basically what I have right now in here. For instance, that's shown to, it's 13 dBm out of the minus 13 dBm out of the DAC. So let's run this system. Okay, so we're going to run this system, and it's going to take about 2 minutes to run. So I'm going to run right now the co-simulations. The co-simulations is going to basically, right now it's running random bits throughout this chain, mimicking the entire downlink generation in the baseband section to the IF, and then outputting the digital IF. Okay, so at the end, what we will see is we're going to see a basically the analysis of the signal. It's going to update these here, which I just showed you, but it will also go in and do the EVM and run this whole sections in here, basically this section and this section here. So it's going to run these right now. It's going to put the signal through the RF chain and the RF chain in here, okay, and then it's going to display real time the streaming of the digital modulations into the RF transmitter. And of course, realize this is what we're doing for is just for a single beamformer chip, okay? This has to be done for 16 channels because we have 16 beamformers, each one of them feeding 4 antennas to make up the 64 array antennas. But we don't need to run it for 16 times because whatever happens once is going to happen with all of them, hopefully, with little tolerances coming from the RF implementation, circuit implementation. So until we get that done, just want to say that, advertise to you that if you have a need for RF training on, you can check my videos. There is a whole set of course that is done for the ANSYS systems, where I basically my videos that you can see in my channel, YouTube channel. I really please you to go in and subscribe to my channel. I need your support in that regard. So this is a course that was done with hands-on, doing RF designs using Cadence. And then I have another training, which is basically for the similar stuff that I'm doing right now, which is the Pathwave SystemVue simulations. And so this is a 3-day, I hold that here in Jerash, Jordan, at one of the hotels, this hotel in here, nice place. So if you feel like you need something like that, let me know. If you have a company that has a number of engineers, I could just, you fly in and attend it here. I design it, customize it according to your needs, or I could fly to your site, wherever it is, whether it's in the Gulf, Saudi, United Arab Emirates, Egypt, Turkey. So please reach out to me and, okay. So I see, okay, so it's running right now, as you can see here. So what we have here is you can see that the EVM in this case, it's running about with an RMS of somewhere around 8, 9. So it's once in a while you get a burst of errors. The SNR is 25 dB. The DAC IF output is running right here, which is very clean EVM, of course, 0.1. Okay, but the SNR is 60 dB. This is the PA here. This is the baseband. This one here is basically let's see. So we're running basically what you're seeing is these here. So you're seeing these here and these here, which is before the RF and after the RF. Okay. So you see the same thing that I just showed you. Now there are other things that you can display. Of course, I turn them off, but you can see the constellations. You can see my computer is overloaded right now with memory, so let's see, it's running slow. Okay, what did I just add it? Okay, here we go. The Q, this is the Q, so this is the constellation. You can display all these things in here. Okay, so again, so that's it, ladies and gentlemen. So basically, we took the RF system that I have done last time, which was designed here, which is the this is the 28 gigahertz beamformer transceiver. I took the transmit path only, which is here, ran the RF, and then did the analysis on it theoretically just to make sure. And then we went into the SystemVue digital signal processing section and added a modulator, an actual modulator, grabbing bits, ones and zeros all the way, and just tracing the signal through the whole entire chain to validate the system. So I hope you enjoy this. Please sign up for my channel if you don't mind me doing that. Please do it to subscribe to my channel. I would appreciate it. And until next video, I thank you very much for watching, and have a great week, day, night, whatever it is at your end. Thank you very much. Have a good day.